Swayam Prabha. Digital India. Educated India.
Dear viewers, in this session, I would like to focus my attention onto some of those special techniques by virtue of which the noise present in the data can be removed. Similarly, the analyst may be interested in identifying the edge between any two class of informations. Rather than performing image classification to identify the extent of information class, the edges may be of more importance. So, I take up the topic on spatial filtering, which allows the analyst to undertake these tasks. Space-borne imagery may have inherent noise or interference due to sensor error or malfunctioning of the detector, channel transmission and sampling error. The noise caused by noisy sensor or channel transmission error appears as discrete isolated pixels variation that are not spatially correlated. This means, the pixels having error often appear different from their surrounding pixels. At times, the edges or boundaries between the features are not clearly discernible, and this creates problem for interpretation of images. Spatial technique, a digital local enhancement technique, can be very useful to overcome the problem. Spatial filtering is a pixel by pixel transformation, which depends on the digital number of the surrounding pixels. Spatial filtering is a context dependent operation that alters the gray level of a pixel at any location according to its relationship with the digital counts of the pixels in its immediate vicinity. Spatial filtering refers to separating out some features. Its task is to either emphasize or de-emphasize image data of various frequencies. Essential spatial frequencies enable the tonal variation per unit area of an image. So, an image area of high frequency is totally rough. This signifies that the digital number values in these areas change abruptly over a small number of pixels. This can be visualized by looking at the graphics given below, wherein we find that at certain intervals a group of pixels are having white tone, whereas some group of pixels are having black tone, but this variation is recorded over a very small number of pixels, and thereby what we see is something like a appearance of a chess board or a checkered board, wherein the image appears to be much more noisy and also rough in nature because of frequent changes in the tone which is present. Conversely, the image area of low frequencies are tonally smooth, and it signifies that the digital number in the images changes gradually over a large number of pixels, that is like a water body. The graphic shown below gives us a clear picture of a low spatial frequency image, wherein we can find that the tone of the image changes from black to white as we move from bottom to top. The bottommost row of elements are depicted in black color. The next thereafter there is a small amount of increase in the brightness and we see a darkish gray, and this continuously reduces till we reach to the top of the image, wherein we find it is totally white. The variation of the tone over this range of image, as a matter of fact, has been so gradual that it gives a very smooth appearance to the objects which are there, and also it gives a very pleasing outlook to the image. Spatial filtering can be categorized as low pass, high pass and band pass filtering. It may be remembered that the first two are more commonly used in digital image processing, whereas the third one, that is band pass filtering, is used in signal processing. Here in this particular course, I am going to focus on the digital images. Thus, spatial filtering processes may be categorized under two, that is low pass and high pass. So, let us look at what actually is low pass filtering. Low pass filtering is used for smoothing or removing the noise. It is designed to preserve the low frequency details at the cost of high frequency details. This particular slide, as a matter of fact, shows that a low pass filter of 3 by 3 window size, as it has passed over a digital image, the edges have become much more clearer in this particular case. Reason being that the mathematical function which has been used here is probably a averaging function, and thereby those pixels at the edges which were mixed pixels, they have been either, depending upon the membership of the kernel, it has been converted either into one class or into the second class, but it is no more a mixed information in terms of the two classes which the edge pixels may be having. So, the appearance of this image appears to be very good. However, if we focus our attention to the two main streams in the central part of the image, in between we find that there is lot of variation or tonal representation is changing very fast. If I increase the low pass filter size from 3 by 3 to 5 by 5, what I find is that in this central part between the two streams, the information now has started to blur. Interestingly, the edges of these streams have also started to blur, and this intensifies further when I use a low pass filter of 7 by 7 window size. Here the information is much more hazy, or you can say it is now more unclear for the analyst. Well, what does this mean? It means that we should be careful when we are selecting the window size for the low pass filter to perform its activity, such that it does not degrade the original image quality. Normally, we prefer to use a 3 by 3 window. However, for other categories of operations, we may prefer to use higher size of the window. Next is high pass filtering. High pass filtering, on the other hand, preserves the high frequency details at the cost of low frequency details. That is, informations which are homogeneous and do not vary over a distance of pixels, these informations would be de-emphasized during the course of spatial filtering using high pass filters. For this same reason, this particular filter is also known as edge enhancement or edge crisping operation. This particular slide shows us a high pass filter using a 3 by 3 window, and what we can see here is a very fine demarcation between any two object boundaries which are there, whether it is between forest or dry sand in the river, or it is the agricultural field and the bare soil. Here one can even see very small edges which are present, and thereby in the top portion, top right portion of the image, what can be seen is that there are many small edges which have been identified, and thereby the image appears to be very noisy, or what we call it as a busy image. When this window size is increased to 5 by 5, well, all the images, all the edges which were seen in this particular image now tend to have a sharp definition of the boundaries. However, in between the edges, the filling up has been ignored, or you can say it has been de-emphasized. When I increase the high pass filter kernel to 7 by 7, now what happens is only the big edges are retained, the smaller ones are removed. So, if I am interested in broad classification of informations, probably a high pass filter of higher window size would yield a better result. The third category is band fast filtering. Well, this is widely used in signal processing. It allows the spatial frequency in a limited region of the spectrum instead of all the frequencies above or below a cutoff frequency. This is applicable only for isolating periodic noises from an image. It is of limited use for thematic applications. In view of the application, the spatial filtering operation are categorized as noise removal, edge enhancement or edge crisping, and edge extractions. Before we proceed ahead, first of all, look at the basic concept of filtering. Filtering is performed using convolution windows. These windows are called mask, template or kernel. The window is moved over the input image from extreme top left corner of the scene from pixel to pixel, performing discrete mathematical function transforming the original input image digital number to a new digital value. First, it will move along the first line. As soon as the first line is complete, it will restart for the second line and continue till it covers the entire image. To carry filtering, a process known as convolution is performed. So, what is convolution? Convolution may be defined as a simple mathematical operation which is fundamental to many common image processing operators. Convolution provides a way of multiplying together two arrays of numbers, generally of different sizes, but of same dimensionality, to produce a array of numbers of the same dimensionality. In image processing context, one of the input array is normally a gray level image, and the second array is usually much smaller and is also two dimensional and is known as the kernel. The convolution is performed by sliding the kernel over the image, generally starting at the top left corner, so as to move the kernel through all the positions where the kernel fits entirely within the boundaries of the image. Each kernel position corresponds to a single output pixel, the value of which is calculated by multiplying together the kernel value and the underlying image pixel value for each of the cells in the kernel and then adding all these numbers together. In this graphic shown below, it shows on the left hand side we have the input data consisting of the digital data, and over this a convolution window or a kernel is sliding over. It is interesting to see that this particular kernel, as a matter of fact, bears a direct relationship to the neighborhood pixels which is surrounding this central pixel. In this particular example, we see that the central pixel value is twice the value of the neighborhood pixels with the opposite sign. If the image has m rows and n columns and the kernel has small m rows and small n columns, then the size of the output image will have m minus small m plus 1 rows and n minus small n plus 1 columns. That is to say that there will be a reduction in the size of the output image after spatial filtering has been performed. So, the value of the bottom right pixel in the output image will be given by the relationship, that is, at the location 057, it would be the product of I 57 multiplied by kernel cell 11 multiplied by I 58 kernel cell 12 plus I 59 kernel cell 13 and so on. So, mathematically the convolution can be written as O I j, where I and j represent the cell numbers, and this is equal to the double summation of k is equal to 1 to m and I is equal to 1 to n intensity values located at I plus k minus 1 comma j plus 1 j plus L minus 1 multiplied by the kernel position cell value k is equal to k I k comma L, where I runs from 1 to m minus small m plus 1 and j runs from 1 to n minus small n plus 1. It may be noted that many implementations of convolution produce a larger output value than this, because they relax the constraint that the kernel can only be moved to positions where it fits entirely within the image. Instead, these implementations typically slide the kernel to all positions where just the top left corner of the kernel is within the image. Therefore, the kernel overlaps the image on the bottom and the right edges. One advantage of this approach is that the output image is the same size as the input image. Unfortunately, in order to calculate the output pixel values of the bottom and the right edges of the image, it is necessary to invent input pixel values for the places where the kernel extends off the end of the image. Typically, pixel values of 0 are chosen for the regions outside the true image, but this can often distort the output image at these places. Therefore, in general, when using a convolution implementation that does this, it is better to clip the image to remove these spurious regions. Removing n minus 1 pixels from the right hand side and m plus 1 pixels from the bottom will fix the things. A kernel window may be rectangular in size, having size 1 by 3 or 1 by 5, or square, wherein the size could be 3 by 3, 5 by 5 or 7 by 7 pixels. Each pixel of the window is given a weightage. For low pass filters, all the weights in the window will be positive, and for high pass filters all the values will be negative or 0, but the central pixel will be positive with higher weightage values. In the case of high pass filter, the algebraic sum of all the weights in the window will be 0. Many types of mask windows and different sizes can be designed by changing the size and varying the weight within the window. The simplest form of mathematical operation performed in filtering operation is neighborhood averaging. Another commonly used discrete function is to calculate the sum of the products given by the elements of the mask and the input image pixels digital number at the same point, and use this sum as the output digital number of the central pixel digital number in the moving window. Having discussed the concept of filter and convolution, now let us start with our major task, one of the major tasks, that is noise removal. Noise is a term used to designate unwanted signals recorded in the image. A noise in an image may be detected as isolated pixels having no correlation with its neighborhood pixels. It may be present in the image due to pre-processing of the data, sensor characteristics or channel errors. If noise is present in the image, then the corresponding histogram will not be Gaussian in nature, and the image is generally found unsuitable for analysis. Hence, noise should be removed from the images so that subsequent enhancement, registration and numerical analysis can be performed on the images with a high signal to noise ratio. Noise can be generally grouped into two classes: independent noise, noise which is dependent on the image data. So, what is image independent noise? Image independent noise can be described by a additive noise model, where the recorded image, which is represented by the function of I j, is the sum of the true image S I j and the noise N I j, and can be represented by the equation f I j is equal to S I j plus N I j. The noise, that is N I j, is often 0 mean, and it is described by its variance, that is square of the sigma. The impact of the noise on the image is often described by signal to noise ratio, that is SNR, which is given by the equation SNR is equal to under root sigma f square divided by sigma n square minus 1, where sigma s square and sigma f square are the variances of the true image and the recorded image respectively. In many cases, additive noises is evenly distributed over the frequency domain, that is white noise, whereas an image contains mostly low frequency information. Hence, the noise is dominant for high frequencies, and its effect can be reduced using some kind of low pass filter. This can be done either with a frequency filter or with a spatial filter. Often, a spatial filter is preferable, as it is computationally less expensive than a frequency filter. Then we come to the next category, and that is data dependent noise. In the second case of data dependent noise, that is arising from monochromatic radiation is scattered from a surface without whose roughness is of the order of a wavelength, resulting in image speckle. It is possible to model noise with a multiplicative or a non-linear model. These models are mathematically more complicated, hence, if possible, the noise is assumed to be data independent. Another type of noise which is very commonly found, and that is detected noise, which occurs in all recorded images to a certain extent. This kind of noise is due to the discrete nature of the radiation, that is, each imaging system is recording an image by counting photons, allowing some assumptions which are valid for many applications. This noise can be modeled with an independent additive model, where the noise n I j has a zero mean Gaussian distribution described by its standard deviation or variance. So, each pixel in the noisy image is the sum of the true pixel value plus a random, that is Gaussian distributed noise value. Another common form of noise is data dropout noise, commonly referred as intensity spikes, speckle or salt and pepper noise. Here the noise is caused by errors in the data transmission. The corrupted pixels are either set to the maximum value, which looks like snow in the image, or have single bits flipped over. In some cases, single pixels are set alternatively to 0 or to the maximum value, giving the image a salt and pepper like appearance. Unaffected pixels always remain unchanged. The noise is usually quantified by the percent of pixels which are corrupted. So, let us look at how do we undertake the process of removing these noise. Well, the filters which are used are known as smoothing filters. These are designed to reduce the noise, detail or the busyness in an image. If multiple copies of the images are available or can be obtained, they can be averaged pixels by pixel to improve the signal to noise ratio. However, the enhancement techniques developed for this can be performed on a single image. In this case, typical smoothing filters perform some form of moving window operation, that may be convolution or other local computations in the window. So, what are the different types of noise removing filters? These are the mean filter, the weighted mean filter, median filter, mode filter, Olympic filter and multi-level median, that is MLM filter, P median or PM filter and adaptive mean P median, that is AMPM filter. Now, let us look at each of these filters in detail. Mean filter. In this technique, each pixel within a given window, say 3 by 3, is sequentially examined, and if the magnitude of the central pixel is significantly different than the average brightness of its surrounding pixels as given by a predetermined threshold value, then the central pixel is replaced by the average value. The graphics below besides shows the layout of a mean filter, where x represents the central pixel which is under examination, and A1, A2, A3, A4, A5, A6, A7, A8, these are known as the neighborhood pixels, and we will be examining these 8 neighborhood pixels and comparing their average value with respect to the central pixel value, which is x. So, this process can be represented mathematically as that if the absolute of x minus 1 by x summation a I, where I is from 1 to 8, is greater than epsilon, which is the given threshold value, then x would be assigned the average value of all the 8 neighborhood pixels represented by the equation, where x would be equal to 1 by 8 summation of a I, where I varies from 1 to 8. If this condition is not true, which means that the value of x does not vary too much, then it is left to have the same value, that is x is equal to x. This particular slide shows the output after applying the mean filter of a 3 by 3. Well, if we recall, the image appears to be very much similar for a low pass filter of 3 by 3. Next is weighted mean filter. A weighted mean filter is often used in which the weight of a pixel is related to its distance from the central pixel of the window. For example, if the processing of boundary area of any region is to be undertaken, then the different weights inside and outside the boundary are assigned, such that the best results for the boundary as well as for the region can be obtained. This is more like a filter wherein we take the square of the inverse of the square of the distance as the weight and use this as the weights for the neighborhood pixels in order to identify what would be the value that should be assigned to the central pixel. Next filter is the median filter. Median filter uses median rather than average of the neighborhood pixels of a given window. The median of a set of numbers is that value such that 50% of the numbers are above and 50% are below it. It is considered to be superior than the mean filter, primarily due to two reasons. First of all, the median of a set of n numbers, where n is odd, is always equal to one of the values present in the data set. Second, median is less sensitive to errors or to extreme data values. Conceptually simple, a median filter is inefficient to implement because sorting of the pixels in the ascending or descending order is required. However, it is one of the best noise removing and edge preserving smoothing filter, but thin lines narrow than the dimension of the filter window may be removed. This particular filter has no user defined parameters. This particular slide shows us a median filter using a 3 by 3, and what we can see now here is that the definition of the edges have become much more clearer. Reason being that in the actual image there could have been a gradual variation from one information class to another information class, and thus the edge pixels may have been belonging to neither of the two classes of the informations. That is, this particular pixel can be referred to as a type of a mixed pixel. By adopting a median filter, what has happened is the real values which are there in the actual data set, that has been replaced, and thereby it provides a good break in the information, which is now crisp and not fuzzy. The next filter is the mode filter. In this technique, the central pixel is replaced by its most common neighbor. This is particularly useful in coded images such as classification maps, in which the pixel values represent object labels. Averaging labels make no sense, but mode filters may clean up isolated points. It produces irregular shifts in edges, which make them appear ragged. The next filter to be considered is the Olympic filter. The Olympic filter is a variant of mean filter. It is named after the system of scoring used in certain Olympic events, where the highest and the lowest scores are dropped and the remaining ones are averaged. The Olympic filter ranks the values within the filter window, that is, number of values is equal to n, and discards the high and the low values before calculating the mean of those remaining. The output of the Olympic filter is less influenced by outlier values than the mean filter, but the averaging process blurs edges and removes fine details in the images. Next is multi-level median or MLM filter. The MLM filter is designed to reduce image noise, that is outlier values, while preserving edges, corners and thin line details in the image. The filter calculates separate median values for horizontal, vertical and the two diagonal transacts through the central cell of the filter window. The minimum and maximum of 4 values are then found. The minimum, maximum and the original center raster values are then ranked, and the median of these 3 values is assigned as the filter output value. The MLM filter has no user defined parameters. The MLM filter preserves edge better than the simple median filter, but does not smoothen small scale noise. P median or PM filter. The P median filter is designed to suppress noise while preserving edges and line details. The filter calculates median values for 2 subsets of the values in the filter window. 1. Combining the horizontal and vertical transacts through the cell center, 2 diagonal transacts through the cell center. These 2 median values are then averaged. The output of the filter is a user controlled weighted average of the average median and the original central cell value. The PM filter preserves edges better than the simple median filter, but provides less noise suppression in uniform regions. The next filter to be considered is the adaptive mean P median, or in short AM/PM filter. The adaptive mean P median filter is a variant of the P median filter that is designed to provide better smoothing in uniform regions, while still preserving edges and the line details. The filter first classifies the central cell in the filter window as belonging to either a uniform region or to a edge region. AM/PM filter then applies the P median filter in regions containing edges, but uses a simple averaging filter in region with relatively uniform values. The output of the AM/PM filter is the edge regions is a user controlled weighted average of the calculated P median filter value and the original cell value. This weighting does not apply to the areas where simple averaging is performed. Here we can now see the output of a AM/PM filter of size 3 by 3, and we can see how well the information has been preserved, specifically the edges. And now we can see even these very small features which are there, they are getting emphasized. In my next session, I would discuss the various types of spatial filters. Thank you.